Sounds great. So everyone, welcome here. And today I'm really happy to have Professor George Kada. Sorry, I'm always
Tzanetakis.
bad for
No worries.
last name. And then, so George is my old friend back in CMU. So when we was in the same intermediate groups in CMU, and then George was graduated from Princeton University, and then he was in CMU as a postdoc, and then he now joined University of Victoria as a faculty member there. So this year he was in Google for Statistical, so that's why he was here give us a wonderful talks on the music retrieval stuff. So it's great. I will give the focus to George.
Okay, thank you very much for the introduction. It's a pleasure to be here. I can't wait to put a Facebook update from inside Facebook. It will make my wife really impressed. I'm going to talk about a few topics, but they're all kind of centered around the idea of analyzing music automatically and then doing stuff with that. So I like to think a little, I always motivate talks like this by thinking about how do you find out about new music? How do you listen to a new music piece? How did you learn about Twinkle, Twinkle, Little Star, or the latest song by Lady Gaga? And in the old days, you basically had to physically be present where the music was performed. Music was a perishable good. You could not capture it in any way. The first step in capturing music was music notation. So then, to some extent, it's more like not really capturing the food, but maybe capturing the recipe for making the food. You could send a recipe to your friend with a carrier pigeon, and then they could sit on their harpsichord and play it. And that was a way to transmit music that was slightly different. And yeah, probably will be better. The slides are dark, so it's probably best with lower light. No problem.
What are some controls like forward lights?
Oh, I can stand, yeah.
So maybe we can choose one more seat. So
Yes.
if you guys want to take some seats.
Actually. Okay, so let me move it. So the next, it's fine, Dark. I don't know, it's probably better. So the next big step was recording. So recording changed everything. We all have grown up with recording being a given, but it's hard to even imagine how it would be to not be able to capture music. But now we have a completely different situation where basically you can, music, instead of being tied to a physical medium, is just bits and bytes, and you can have them anywhere and everywhere. And what I view as the not so far future of this situation is that sooner or later, all of recorded music will be available to you in some form. So already companies like Apple and Google and Amazon are offering music services that allow you to have something like 5,000 or 25,000 songs. And from the perspective of the company, they already have access to millions of songs. So the question is really, what do you do with that? How can you meaningfully understand, explore, discover new music, play around with such a gigantic collection? It's easy to do if you have a bunch of CDs in your car. It's easy to pick the music you want. But if you have this unprecedented access to this vast universe of music, what do you do with it? So I've been working in this area for a scary 10 years, which it feels like yesterday. But anyway, before 2000, there wasn't a lot of stuff. I mean, before 2000, it was hard to find a computer that could play music. Most computers didn't have sound cards built in, and hard drives were 20 megabytes, which hardly fits a single song. But starting in 2000, there is quite a bit of academic work. There's about now 10, 11 years of a conference called ISMIR. That's the International Society for Music Information Retrieval. And there's an increasing presence of academic work in this area. But as usual, academia usually, hopefully, does things a little bit earlier than industry. And if you look at the number of songs sold on iTunes, this is on the iTunes store. It's starting, where was it? It's hard to see the dates. I think it was to 2009. This graph is from like 2004 to 2009, and it shows how quickly. And these are, you know, in some sense, it's a small subset because these are the legal purchases. These are actually the suckers who paid 99 cents at iTunes to buy music instead of downloading it free like some of you might be doing. So there's a huge amount of digital music out there, and of course people have started looking at it, and there's industrial interest. iPads, iPhones all have a strong music component. There are startups like Echo Nest and Pandora and Last.fm, and there are bigger entities. Google had a first effort in music in China that was only released in China, and recently in the last 2 or 3 weeks they released Google Music, which is another system for sort of playing around with music. So it's a very exciting area. At least to me, and I've been working on it for 10 years, but it's quite exciting seeing it grow from an academic curiosity where everyone was asking me, why are you doing this, to the point where I don't even have to have this introduction anymore. I could just say iTunes, Genius, instant mix in 3 words, and you would know what I'm talking about. So let's move on a little bit. I definitely don't want to do a class in audio signal processing here, even though I love audio signal processing. But you know, at the heart of a lot of these things is basically something called the short-time Fourier transform, which essentially you can think of as analyzing sound in terms of building blocks. Each building block is basically a simple sine wave. So by looking at sine waves and how these sine waves interact and at what proportion they are, you can tell a lot about the music signal. So I've spent a significant part of my research work working in audio feature extraction, basically techniques to take a time domain waveform, which is how audio is represented, and extracting some summary information that captures something about that audio. So if you're washing the dishes and you're listening to radio, and the radio switches from playing you know, some tune by Lady Gaga to playing some classical music, you notice that change. It's sort of a very, even if you don't know the song or whatnot. So this is a very rough kind of perception of music, but it's something remarkably challenging to have a computer do. It's one of those classic cases of problems like face recognition or speech recognition where we are extremely good at doing them. A 3-year-old can do them quite accurately, and you need sort of state-of-the-art audio signal processing and machine learning to even approximate that performance. So audio is extremely data intensive. So to store 1 second of audio, you need something like 44,000 numbers. So the process is one way to think of it as a way of analyzing audio in terms of frequencies. So this is an orchestral piece, and here's a flute line, and that's not at all apparent from the time domain waveform. It's questionable whether it's apparent from the spectrogram, but at least you get a little bit of a better sense of what's happening. And then we take that, we apply something called the Mel frequency Kevstral coefficients. We take a 1 second window, compute some dynamics and statistics, and we get a feature vector. So at the end of the day, when you do all that stuff, you get sort of 2 alternative views of a piece of music. One view is that a piece of music is a sequence, a trajectory in space of feature vectors that changes over time. So you can imagine that if you have a piece of music that starts with a calm introduction, it might be in one area of the space, and then when the drums come in, it goes in another area of the space. And another viewpoint is that your music lives in a high-dimensional space, and each piece of music can be represented as a point in that space. And that's the representation that is used by most content-based music analysis systems or recommendation systems. So essentially so Google Music has a feature called Instant Mix, where you provide a seed song and you get back a playlist that's similar to that seed song. that works partly by looking at metadata, so saying that this artist is related to this artist, but also looking at the actual audio. So for example, if you take a mellow track by U2, it will find other mellow tracks of artists that are related to U2 rather than finding an upbeat track. So it's important to analyze the audio. And the way the audio is represented after a long pipeline of audio feature extraction and machine learning is as a vector of something like 100 numbers. So as far as we're concerned in this talk, each piece in your music collection is a vector of 100 numbers, and you can view your entire collection as a cloud of points in that 100-dimensional space that is hard to visualize, but we can deal with it numerically. By the way, if there are any questions, comments, feel free to jump in. There's no strict set of slides I have to go through. So,
sorry, quick question.
Yeah.
So a feature, is that something you could describe in words? Is it just something that comes out of machine learning? I mean, a given feature is not like loudness or like. Yeah,
some of them have they have names, like spectral centroid or loudness of the fourth Mel frequency band, but they're not exactly perceptually transparent. Okay. So typically you put a layer of machine learning on top of that, maybe for training tags or for doing similarity to get the thing. So it's not, you don't know exactly why, but it kind of combines these things. Sure. So I like, this is a little bit self-bragging, but I like to show this slide. This is a slide from my PhD thesis, even earlier than my PhD thesis. And it's a content-based music information retrieval system with a collection at the time of 3,500 clips. It was just my own collection. And it does basically instant mixing or playlisting without using any metadata, just by analyzing the audio. So as far as the algorithm is concerned, all audio pieces are equal. Like, it would just be like shuffling. It doesn't know anything about artists or genres. So if you listen to some of these pieces, if you listen carefully, so that's the query, and then you get back, oops. You get other songs by Bob Marley. But it's important to remember that the algorithms knows nothing about Bob Marley. Somehow, by taking all these features having to do with analyzing the audio, it matches them. And one thing that I threw under the rug is that there are also features related to rhythm and also some features related to pitch content. Yeah.
Did your thing also return stuff from other reggae artists who weren't Bob Marley, or?
Yeah. I mean, as far as it knows, it doesn't know the difference between those two. It actually just happened that the only reggae I had in that collection was by Bob Marley.
So. Hey, what happens if a song changes completely in the middle?
That's a very good question. In general, things fail, and they still fail 10 years later. For various reasons, people tend to use a single feature vector representation for the entire thing. So they typically will use something like 30 seconds. And in general, it doesn't work really well if you have large songs with many different sections.
But if people were to use the other representation as like a feature moving in space, they would be able to...
Yes, you could do that. That's much more costly. And it's also not clear how to define similarity in that case. But yeah, there is work in that area. For sure. So it's all these, I could play all these examples. They pretty much do what you expect. Like the returned results are kind of what you expect. It's more interesting to look at the cases where the system sort of does weird things. So I tried to find some examples in my collection that would challenge it. So I'll just play you one. This is at Princeton, there's a composer named Paul Lansky who does a lot of computer music, and he was part of my committee, so I just wanted to kind of make him feel good. So I got a piece that he has written, which is for processed voices. That sounds quite unique in a sense. So, you know, imagine a normal collection of music. What would match with that? That's what we're trying to find here.
This is the way to live in this world. Everyone loves
So we can argue about how good these are or how lame, but I find them interesting. I think it's actually quite a reasonable choice. Here's another one. And here are the returned results. So one thing to sort of, I should mention is that music is not a search problem, really. It's more a discovery problem. And the easiest way to think about it is think about the iPod Shuffle, right? Imagine if you're sort of, what are they called? Kindle, your ebook reader would give you a random shuffle of all your books at every time you turn the page. It would sort of be kind of weird. But that's what people do. Like, you know, that's how you listen to your music. You just shuffle it. So we're quite tolerant. So having a little bit of support so that you don't, what has happened to me is one time I was running a marathon and I was just getting to the last part of the finish, actually a half marathon, just close to the finish line. And I had my iPod. It was playing some Led Zeppelin. I was all charged. And it just suddenly switches on shuffle to this like really slow ballad tune. And I'm pressing, you know, sweating, barely able to run, pressing the skip button, hoping to get some, you know, good energy song. And I ended up finishing on some really slow song. But, you know, that's where we're moving to. So, so I should mention back here that these searches were simply done by doing nearest neighbor search in that high dimensional space. So you pick your seed song and you just find the closest songs in that 100-dimensional space. For any of you who have done stuff in machine learning or data mining, you realize that if you have such a high dimensional space, it's pretty easy to do supervised learning. You can build classifiers. There's all sorts of classifiers, Gaussian mixture models, support vector machines. So I'm not going to go over that, but basically you can build a system that listens to music and classifies it in real time automatically. And again, this is just to give you a flavor that, you know, things that now are becoming mainstream academically were explored maybe 10 years ago. This is a demo. Let's see if I can context switch enough to get it. Yeah. So,
You're running out of battery.
oh, thank you. Exactly. So this is live real-time genre classification based on. Oh, you have it. Yeah. So these bars go up and down in real time. So rock music, classical music goes up. Bach. And this is all done in real time. The idea is that we would get the radio stream. So now speech.
They eat broccoli by the ton.
Speech goes up, and also hip hop, which sounds like
There's no
speech,
certain place that
goes
Dominic
up.
Foster's put it. You know, maybe you put it as the dominant thing on their plate.
I don't know. We all.
So you get the idea. So there's a lot of cool automatic analysis that can be done. So now let's move into into some more recent stuff since then. So one of the main changes that has happened in all areas of multimedia retrieval has been the switch from sort of fixed hierarchies to free-form taxonomies and tags. So for anyone who has used Flickr or Last.fm, basically you just pick random words that you think describe your item and you label them. So you have free-form tags. There's no imposed structure. And what that means is you have things like synonyms. So some people might label the track as female voice. Some other users might label it as woman singing. So in terms of machine learning, this is a multi-label classification problem with some twists. And some of those twists are synonyms that I already mentioned, subpart relationships. So maybe string quartet is a subpart of classical music, but when you get the tag vector, they just are tags. You don't know that. You have to somehow recover it. They're pretty sparse. And they're noisy, and also you don't know, absence of a tag doesn't necessarily mean that that tag doesn't apply. It might mean that someone just didn't put that tag yet in. So, and even the more extreme cases, the so-called cold start problem, if I release a new track of music into the internet, it has no tags. So until someone starts tagging it, I can't get any information about it. So what we want to do is we want to automatically suggest tags. That's pretty much the problem, and hopefully make them relatively meaningful. So in many cases, if you look at the literature, each tag is treated independently as an individual classification problem, a binary classification problem. Is the tag present? Is it not? You train a model, and you classify it. There's also the inverse is interesting, is what's called query by keyword. So you could say, you know, I want a playlist that has female voice, jazz, ballad, whatever. So I'm going to mention one idea that is actually used quite a bit with different names. There's no consistent name, which is called stack generalization. And the idea there is that you have a one stage of classification which is then used as an input to a second stage of classification. So basically, at the first pass, you get a probability for every tag. How likely is that tag to be present? And then that probability vector is used as input to your second stage. And if you do that in traditional classification, you get small improvements. But when you do it in tag annotation, you can get much more mileage out of it. So this is the idea. First stage, each tag, you train a support vector machine with probabilistic output. Second stage, you use that affinity vector as input to another SVM with probabilistic output, and that takes into account tag dependency. So I don't want to spend too much time on machine learning in this, but I'll try to explain the intuition. Suppose you don't have enough pieces of music labeled as opera to train a classifier for opera. But you do have a lot of examples of male voice in classical, and you have a lot of examples of female voice in classical. And you notice that all the opera examples have those two as high spikes. So basically, the idea is to use the information of tags that you can do well to infer tags that you don't do so well. And that second stage classifier takes as input the probabilities of the individual tag classifiers and will work much better. So if you have done some work on retrieval, there are some standard measures like ROC and F measure, and you can basically show that you can get almost a 1% increase by using this approach, or in terms of ROC about 0.1, and so basically it helps. And here is a demo of the system. Let's see if I can jump out. Oh, wrong. Okay, that server is not working. Okay, so basically, it's also on the static image. The only difference is that you won't be able to hear the audio. What am I? Oh, I see. So basically, what you get is you get a piece of music. This is a piece by AC/DC. Does everyone know that group? Sort of some old people that make really noisy music. So this is the ground truth in the green, and here are some examples. So it's angry, aggressive, exciting, thrilling, powerful, strong, classic rock, drum set, male lead vocals, not soothing, not mellow, not romantic, not sad, not soft, not loving. And
what's the difference between the green and the non-green?
So this is the ground truth, what people have sort of labeled. This is what the classifier has done. In green are the ones that are common between the two. So it's sort of the overlap between the prediction and the ground truth. And here you can see things like, you know, it says something, okay, it has some stuff that's kind of not right, like there's no harmonica in AC/DC as far as I know. But there is a bass, and here there's no bass. But that's what you expect. But it does a decent job, okay? So this is, so far I've sort of described kind of what I would say a data mining, machine learning approach to the problem of music recommendation. And it's something that's still going strong. A lot of people are working on it, including me. So now we're going to switch gears a little bit and go to something slightly different. So the first thing I want to have is a simple observation, which is that in music, in any kind of similarity space, context matters a lot. So if you are a young teenage girl, then, you know, and I play you, let's say I play you these clips. Actually, I'll do it the other way first. Suppose you are a jazz fan. If you are a jazz fan, you know that who is Billie Holiday and who is Ella Fitzgerald, and they're almost like the two opposite ends of what a jazz singer can be. I would actually claim that any female jazz singer can be viewed as a linear combination between Ella and Billie Holiday with appropriate weight. So, you know, if you hear Billie Holiday, very sort of mellow, sad, melancholic, nostalgic. And Ella Fitzgerald is just like a volcano of energy. And, you know, full of happiness and brightness and whatnot. Now, if I try to explain this to a teenage girl, no offense, they, you know, these are just all black singers singing jazz. You know, to them, what's very different is Christina Aguilera. So that is really that's music, not the other crap. So this is a subtle point, but what I'm trying to say here is that the distance between those two singers, if you view that as if you just project everything to this giant sky, high-dimensional space in the sky, then the distance between those two will be the same. It will just depend on where those 2 points lie. But that's not right, because for a jazz singer, they should be very far apart. For a teenage girl, they should be very close. So how can we get this context information? How can we get things that are more personalized to who you are, rather than sort of one global notion of similarity? And what I'm going to talk about is sort of a 10-year attempt to address this question through visualization. So what I will try to explain is how we can do some visualizations where the thing that you see doesn't depend only on the music that you're listening, but on the music that surrounds it. So my vision is that this holds an enormous potential to return music to being a process where you actively engage rather than passively listen, and lead to unknown music discovery and so forth. So if you look at traditional audio user interfaces, including the sort of stereo visualization I was showing in the beginning of the talk, they're pretty cool. They have waveforms, they have spectrums, they have multiple channels. DJs like to use them in Ableton Live or whatnot. But at the end of the day, they don't know anything about what they're processing. You can't say, find me where the saxophone solo is. You can't say, where does the singer come in? They don't know. All they know is that it's a bunch of numbers that you can draw them on screen. So what we wanted to do is convey some more information that's meaningful in the user interface. So you can do simple things, and like, for example, map frequencies to colors. So if you see something like that, this is a pattern where you have a bass drum and a snare drum. So like boom, boom, boom. You can't see it in that. If you color the frequencies, you can see it. No big deal. Another idea is to have some kind of space where you can arrange your music. You can place points in that space, and each point corresponds to a piece of music, and you sort of make your own arrangement, kind of how you have your desktop and you organize your folders. You just manually place the songs. So that's early work. Later on, I've worked on sort of 3D displays where each kind of 3D object is a song in your collection, so you can sort of navigate through that. Here is an example of mapping music over time in color. So you can see that this piece of music has two parts. One part that sort of looks similar to this color, and one part that looks similar to this color. And because our visual system can take that information in right away, you see that, whereas if you were to listen to it, it would be much harder to see. So the idea is just to move and have some ways of visualizing music that show the structure and show how things change and things like that. And Sanjeev here will remember this, but this is the famous display wall at Princeton. We had this nice toy to play with, and this is showing that system. And you know, we're kind of moving in the wrong direction. Like I was hoping I would have that in my bedroom by now, but instead you get a iPhone. Go figure. That's why you shouldn't listen to any prediction I say, because I had no idea that this was going to happen. Okay, so here's another attempt at visualization. This is something called self-organizing map. And it's a sort of method that tries to use biological principles to organize data. So the idea is that you take your high-dimensional, 100-dimensional space, and you try to project it not to a lower dimensional space, but to a grid. You can think of it as a chessboard. And the way you do it is you assign to each of these squares, you assign randomly a value, and then for every one of your points, you project them to one of those values. And when you assign it to one of those values, you change the weights surrounding that value and that go in that value in such a way that it's sort of more high-dimensional vectors that are close to it will fall nearby. So it kind of self-organizes the high-dimensional space and does both clustering and dimensionality reduction at the same time. So this might be a little bit clearer with an example. Suppose this is given as input an image of random pixels. So you just generate random numbers between 0 and 256, and you get this random picture. And then you run the self-organizing map by taking Euclidean distance between those pixel values. You get something like that, where you have these sort of nice patches of color. One thing that's important is that the exact positioning of those patches might change. Like if I run it another time with the same input, maybe the green will be down here, but kind of the neighborhoods are preserved. So it looks like a pretty neat idea to try out, and it's been tried out. So in 2002, Elias Pampalk, which later went to work at Last.fm, proposed this visualization called Islands of Music. And the way you can think of it is that you project everything to that grid, and then squares that get a lot of songs become higher, and squares that don't get as many songs are lower. So you get kind of a surface. And if you color things that are above a threshold as mountains and everything rests like ocean, you get this islands of music visualization where you have sort of certain areas. And these correspond to sort of songs that are stylistically similar or sound similar and whatnot. So that was the Islands of Music visualization, very nice work. And that inspired me to work on something simpler, which I will demonstrate, which is a two-dimensional, it's the same thing, instead of, it shows the data more directly rather than putting the nice mountains and oceans. And the reason I was interested in that is I was really, at the time, interested in touch surfaces, touch tablets, things that you can navigate by touch. So I'll do a quick demo of this so that you get a more intuitive feeling of how it works. Sorry, this is not more streamlined, but it won't take too long. So now you can click on this thing. So I'm clicking on this square. Here's some blues music. Click again. Another piece of blues music. If I click down here, you get some heavy metal. So you see, it's sort of, just by playing around, you can kind of, if you're not looking for a specific artist, you can just click in a few places. When you find a place you like, you stay. One thing I didn't like about this, and I don't like about all interfaces for music discovery, most interfaces for music recommendation that I have seen, is that they're very computer-like. Essentially, when you browse iTunes, what you're doing is you're having a spreadsheet with a music player. It's really a spreadsheet. You know, you're not playing an instrument. So I like immediate feedback. So one of the first things we did is we changed this so that instead of clicking on the squares, you can just move your mouse around or your finger around and music changes right away. So here's that mode. Oh, I really like this. Oh, so nice. And you know, it's again much more discovery. It's much more entertainment. It's less search. Here is another thing you can kind of see. So here is what I did is I took the genres of the music, and the self-organizing map is organized without knowledge of the genres. But then for each square, I visualize the mixture of genres in that square. So you see that this square is all jazz, but this square has a piece of classical, then a few pieces of jazz, and then one piece of rock music. So let's maybe see what that is. I don't know. I haven't heard it for a while, so I'm curious. So, okay, kind of. So one is classical, the other is jazz, but they're, you know, you can tell that they're sort of similar. Now this is a rock piece. So arguably, you know, maybe you think that's too much, but you can tell that there's something acoustically similar to them, and that's kind of interesting to me, is that you get this extra dimension. You can always put metadata and genres, but you get this nice thing. So you see that sort of it does the job of self-organizing. Now, suppose you show this to a user.
A quick question.
Yeah.
But on the prior one, which was just grey, black and white,
yeah.
What was like the darkness?
The darkness is the number of songs in that square. So when you show, can anyone guess what users say when you show that to them, or you have them demonstrate? Cool. Cool. Okay. Any after the cool factor is gone? I'll tell you the two most common questions. I'm surprised that you're not asking them. Maybe actually people are finally ready for this. But the first question is, what's the x-axis and what's the y-axis? And the answer that it's some nonlinear projection from a 100-dimensional space to a 2-dimensional grid that preserves a locally topologically neighborhood somehow doesn't fly. So that's one question. The other question is, if I want to find Let It Be by the Beatles, or if I want to find Broken Romance by Lady Gaga, how the hell do I do it in this interface? Do I have to find the right square and then click multiple times? What if it's in the square to the left or to the right? So that's something we struggled with, and I have some proposals for how to solve it. But before we go there, we have tried this with all sorts of controllers, from touch surfaces to iPhones to Wii's. We probably will do a version with the Kinect soon. And we have also used it for assistive purposes. Maybe I'll show it in the end because we're running out of time. But this is Dan, who has cerebral palsy, and he can only control the keyboard with his mouth, so he can't use his fingers. So using an interface like iTunes is really hard for him to find music, whereas this one, he can very quickly learn that this is the corner that has one type of music and browse much faster. So that's another dimension of sort of these interfaces that are more direct. So the next iteration, we thought, okay, we have these colors. That was inspired by our colors. What if we put some text over? Like, here is some classical. We'll put the text of classical, and then you will know that this is the corner of classical rather than learning that mapping blindly. So, and the way we do it is that if you think of any tag, whether it's a label or an artist or a free tag, it's essentially a cloud of points in that high-dimensional space, which means it's also a cloud of a set of points in that grid. So if you take their weighted average, you can find the centroid, and then you can position the text at the centroid. You have a little bit of problems like overlap and font sizes, but anyway, it seemed that it was a good idea. At least you get some information of how your space looks like. And then, it took us 1 or 2 years to finally figure out that what if we made the grid disappear completely and make it kind of invisible to the user? And this is pretty much what I have been building up to in this talk, which is the self-organizing tag cloud. And here you can see that, so this is showing a tag like flute. These black songs are all flute, and these black songs are all electronica. And you can see, actually, so you can see that the flute will move from the center, if you had randomly placed points, to one or the other direction. So if you do that, you get something like this. And I want you to notice a few things. One is that, okay, you get some clusters like opera, men, monks, voices. Then here, heavy metal, loud, punk. Here, drumsy, funky, electro beats. So you get these kind of clusters. But also you get some things that are kind of in the middle, like singing. But that makes perfect sense because there's a lot of different singing. So there are points all over your space that have female voice. So basically, all your clouds that are not, all your tags that are not related to content end up being kind of in the center, which is okay. You can still access them. And the clouds that are more differentiated in terms of content get pulled in the corners. It looks a little bit messy, but fortunately, people in HCI have dealt with this problem. What you do is you pretend that each text is a small mass, and you attach strings to them. You run a little bit of a physical simulation pushing them out, and it pushes them out, and it looks much better like that. So now you have this tag, we know how to deal with tag clouds. If I want to hear a piece of music with flute, I click on flute. Nobody has ever asked me what is the x-axis and the y-axis on a tag cloud. So that's really nice. I really didn't like that question.
Our songs, they're not exclusively categories, right? So if you click on singing, you may get the same song, but also you would get clicked on.
Correct.
Opera.
Yeah. There's an even extra advantage, which is that because everything is positioned based on this song space, or clouds of songs, you can have unrelated pieces of information like artists and tags have a correspondence in the space. If I did artist similarity tag cloud and tag similarity tag cloud, you would get two tag clouds where the tags that are close are similar, but there would be no relation between them. So we call that faceted. And here, for example, you might not know at all what ensemble Sretini is, but because you see that it's close to where MARSYAS are, you suspect it's some kind of male vocal monk singing. So it's sort of a nice way of associating things that you know and you don't know. So it solves two problems: tags that you don't know what their meaning is, something like electro funk or whatever that you're not familiar with, and also artist names that you're not familiar. So it's a nice exploratory space. We use this collection called Magna Tagatun and so forth. So, is there a question? Okay. So moving forward, the next part is putting a little bit more context. So existing recommendation systems recommend music solely based on your listening habits, collection, store purchases, content analysis. But given that, you are always recommended the same music. So what is missing is context. If I am studying calculus, I don't want to listen to AC/DC, or maybe I do want to listen to AC/DC. But when I'm at the gym, I do want to listen to something else. And the point is, could we somehow take location and time information? With a desktop computer, you can't, but with a smartphone, you can. A smartphone knows where you are most of the time, and they have this information. So here are some approaches to music playlisting. So the lazy approach, which is what most of us do, including me still now, is skip and shuffle. You listen, you shuffle. If you don't like it, you skip it. Some OCD people do manual playlisting. They actually create manual playlists, move songs into them, and have dinner playlist, girlfriend playlist, whatever. I've yet to meet these people. The new kid on the block is automatic playlist based on seating. So that's like Apple Genius or Google Instant Mix. And these can use content information, music, collaborative filtering, metadata, but at the end of the day, they always give you the same thing. Geo-shuffling was a prototype idea we proposed where we track location and time and skips, and that's the only information you have. So basically the idea is that if you are at the gym and it plays you some classical music, you will skip it. And if you do that a couple of times over time, it will figure out, number one, you are at the gym, and number two, that when you are at the gym at that time, you tend to not like classical music. So you will never have to explicitly seed or do anything other than skipping and listening, and it will learn the patterns. So basically, this is what this slide says, and all you need is some relatively simple path learning, location merging, identification. Google already has that. Can't remember what it's called, but it basically tracks sort of your commute and things like that. So if the shuttle takes a slightly different route, it still knows that you are commuting to work in the morning. So once you know that, then you combine that information with a content-based recommender, and you have your system. So that was what we call GeoShuffle. And we also put self-organizing tag clouds to show your mixes. So here's a mix of new age, classic, folk. This is a particular playlist, a different playlist, and a different playlist based on different times. This was work with a wonderful colleague who unfortunately died tragically a couple of months ago, Scott Miller. So that's why I have his picture there. He was a PhD student, future postdoc that never made it to the postdoc part. So, so that pretty much ends the sort of meaningful content of the talk. But I did want to leave you with some more cool stuff. So I've been working in parallel with that stuff for a while in this idea of robotic musicianship. So we're working with acoustic musical instruments. So imagine a drum that can be actuated digitally. So it has something that hits, and you can send commands to the arm that hits, but the sound is generated acoustically. And we also have acoustic instruments played by humans that have sensors. So for example, if you're playing a guitar, you know which string you're playing, or something like that. And what we want to do is combine these two in an improvisational setting. So improvisation requires music understanding. So you need to be able to check if you are playing too loud. You need to be able to recognize what the other musician is playing. You need to be able to track the time. You need to be able to create variations and all that stuff. So what we are focusing in is how can we bring these techniques of automatically analyzing music into the realm of music performance. And these are some of the robots. This is my former student, Ajay Kapoor, who is now faculty at the California Institute of the Arts. He's a sitar player. These are some of the robots we have built. And what's also really interesting is the software that's driving these things. So the plan is I will finish off by showing a couple of videos of those. But before I do that, I just want to do a little bit of advertising. A lot of the software I showed today, including also the panning visualization and also the self-organizing map with the colors, is written in MARSYAS, which is an open source package for music analysis, retrieval, and synthesis. And if any of you have an itch to scratch and have a lot of free time, since you don't do too much programming here at Facebook, again, you want to spend a lot of time working on something that doesn't pay, you are welcome to join MARSYAS. So, final, out of my presentation. Yeah, why don't I show you some videos? Basically, the final thoughts are that I hope I have convinced you that there's a lot more to music information retrieval than just recommendations and simple batch analysis. And it has the potential to be a much more interactive process. And anything? Yeah, that's pretty much it. And then there are several publications. These are a small subset of them that describe the things that I talked about if you want to learn in more detail about how they work. So now I'll show you some videos of robots in action playing music. So.
It's almost, I always like thinking of it as like a Indian goddess with multiple arms. So you have your two arms playing your regular instrument that you're used to, or traditional instrument, then you have these other arms that come out and play like the other robots and the other things.
We name all the different robots crazy things, depending on our whims for the day, I guess, when we build them. Greatbot is the drum set. It has a snare drum and two cymbals. There is Tammy, who is a marimba bot and a percussion bot.
I think of these things as more machines than robots. They're robotic in the means that they are, digitally enhanced machines. But they are machines, they are instruments in their own right, and the musicians that play them would be, like it would.
This one gives you an idea of how they look, but I'll play you some real music with them. And to me, what's most interesting in this thing is the intelligence running behind what actuates the robot. So if I'm successful. Okay, so try to listen carefully. You will see that Ajay, who is a sitar player, is speeding up, and the robot is speeding up following him. And this is not pre-recorded, this is improvised. The head bobs in rhythm with the music. So you can hear it speeding up. you get the idea. And I could go. This is using a real-time beat tracker that uses Kalman filtering, and you could spend a whole lecture on Kalman filtering on that. But this is kind of what I really enjoy doing, is sort of bringing these worlds of music performance and music understanding and content analysis, signal processing, machine learning interfaces, all in a nice kind of salad. So thank you very much for having me here, and happy to take any questions.
Okay, so I have a following question. Let's say we have two identical songs, recorded like identical, but files is different. Can we match them?
Yes, so there's a whole sort of set of technologies that go beyond simply counting their file size. So there's what's called audio fingerprinting or audio identification, in which case you're matching the exact recording. There's also something called cover song detection, in which case you're matching recordings that are the same piece of music, but by different artists and different performers. And there is sort of noisy fingerprinting that is done by, like, Shazam is an example of a company that does it on cell phones, where you hold your phone in a noisy bar and there's some music playing, and then the phone sends you a text message of what the song is. So there's a whole set of technologies like that, yeah, which I didn't talk about.
Do you think it would be possible to tell if a piece of music was good? As in, like, popular or just my version of good?
Yeah, that's a very good question. So personally, I don't think we are there yet. There are a couple of claims in the news, and the startup that predicted, who was it, Norah Jones would become a star. It's all BS as far as I'm concerned. And when you test it scientifically, you can't find it. So it's really more like these recommender systems are. It's like they can tell you this is a Mexican restaurant. They can't tell you this is the good Mexican restaurant. However, there is a different dimension of quality that I think we can do, which is just simply quality of the performance. For example, the recording quality. So with a lot of these recommender systems, you have no way of separating the version of the song by the famous band from the cover version that the high school band is playing, other than the metadata. But the part of the difference is that the real song sounds much better. It's produced with better techniques, better stereo mixing and stuff like that. And that's something we can probably get a better handle. So more like production quality than musical aspects. You might be able to do something with, like, there's work on singing and karaoke and auto-tuning where people are working on it. I've done work on music, like instrument tutoring, so learning the violin, but nothing that would, tell you this is going to be the greatest hit. Yeah.
For the robot, robot drum was playing in there. How did you decide what drum beat to play? Was it deciding to do that on the fly, or was it only figuring out what beat to play a pre-recorded?
Yeah, so there's the official version and the unofficial version. So the unofficial version is like, as in any music performance, you do what's working. So some parts of it are pre-recorded, some parts of it are less pre-recorded. But in the sort of what we wanted to do, and parts of the performance do have that, is that the robot has a set of rhythmic patterns that are stored and can be played at, because they're stored, you can adjust how fast they are played. And then the tempo tracker decides how fast they are played. They do not start at any particular location. They kind of just come in whenever. And the other interesting aspect is how you teach those patterns. So initially, we had a system where you were hard coding kind of drum loops, but that kind of became tedious. And then we built a system where an actual musician can play a rhythm, and then it analyzes that rhythm and stores it. So you sort of teach the robot by playing to it.
So how does it decide which one of those to play?
Oh, it does some sort of form of matching with the rhythm signal that comes from the sitar playing. Okay. So it uses dynamic time warping, if you want technical details.
Is there any work being done like a smart skip button that goes to either what you were listening to before the skip or just somewhere completely different than what you're skipping from?
Oh yeah, I forgot to mention that. That is the coolest feature. That's what I really want you to remember. Because if it becomes a feature, I want you to remember that the first time you heard it was here. So this was a great idea that Adam Tyndale, a student of mine, had for a project, which was, in most recommendation systems, you get sort of what you like, but you have no way of expressing what you don't like. That's a kind of standard thing, you know, like buttons tend to be pressed more than dislike buttons. But really, in some sense, in most cases, most of us are pretty tolerant of what we listen, except that there's some stuff we really hate, right? You don't want to hear Kenny G. So the idea of radio shuffling is in the iPhone. Shuffling works by shaking it, right? So, but because you have accelerometers, you can measure the amount of shaking. So if you like it, you know, you shake a little bit and you sort of hear a small radius from around where you are. If you really hate the song, you just bang your iPhone down and play something completely different. So that's the radio shuffling. And again, going back to this issue of personalization, the whole point is that because you're doing it for your specific collection, what you like and what you don't like is defined by kind of your skips. So that's the shuffling, sort of proportional shuffling or radio shuffling. Yeah.
Have you ever considered human emotion as an input to the shuffling?
Yeah, so there's a lot of work. Actually, there's a recent even book. It's not a full book, but an edited collection of chapters on emotion recognition in music. And typically the paradigm is you have some user study where people rate songs in some emotional space, typically a valence, arousal sort of space. And then it's a sort of two-dimensional space, continuous space, and then typically the machine learning paradigm is regression, and then you train two regression models, and it works sort of. There's an iPhone app called Mood Agent, I think, that does playlist mixing based on moods. I haven't tried it. But... Okay.
Thanks, George.
Thank you very much.